vapor pressure of solutions of solids in liquids. We have already done the solutions in which we have a liquids in liquids, and we have seen that since liquids are compared with the liquid solvents, the liquid solutes, they are found to be basically volatile. But when we are talking about solids in liquid solvents, one thing is very clear in our mind, that these solids definitely are having higher boiling points than these pure liquids. That is why they are solids. So they are actually non-volatile. They will not evaporate easily. They will not volatilize easily. So they are called non-volatile. Now what happens when such type of solutes are added to the liquid solvents? Like we can take the example of the addition of a sugar to water, or of a NaCl to water, or of a glucose to a water, or of a urea to a water. All these are the examples in which what we are doing is we are adding a solid to the liquid solvent. Now what happens is, now in such cases what we find is, like if suppose this is the solvent, liquid solvent we have, and to this the B solid solute has been added, what happens is, it becomes, both of these are homogeneous in nature, they form a homogeneous solution, and what we find is, now the B and the A molecules all are present at the surface. Both of these are present at the surface. So the surface area available with the A molecules to escape to the gaseous state or to the vapor state will become less. Remember, the B will already not evaporate, or it will not vaporize. The reason being, it's a non-volatile solid, it is already a solid. So in the solution what we find is, it will be only the molecules of A that will evaporate and will go into the vapor state. And that too because now the surface area available for evaporation is less with the A molecules. Less of the A molecules will evaporate. So what will happen is, when the solution is formed, we have less number of A molecules in the vapor state than there in the original case when the solvent was present alone. So what we find is, therefore, vapor pressure of solution decreases and is less than pure solvent. So what we can write immediately as PS is found to be less than P naught A. The vapor pressure of the solution having solid solutes in the liquid solvents are found to be less than the pure solvent. The reason is because the surface areas available for the evaporation to the solvent molecules becomes less, because now the B molecules are also available on the surface. And already B's are solid, the solutes are solid, they are not going to evaporate, they are not going to vaporize. So therefore, lesser molecules of A are available, lesser is the vapor pressure. This is the basic case, and this is the fact. The vapor pressure gets lowered. Now, if we have to find out the vapor pressure of the solutions in this case, as per the Dalton's law of partial pressure, we know it has to be PA plus PB. PA, PB are the partial pressures of component A and B. We know there is no BB because as such B is a solid, it is not going to do any kind of contribution. So we are left with only what? A. Now, we know as per Royle's law, the vapor pressure of volatile component is always, like in this case it is A, is proportional to its mole fraction in the solution, as we have been knowing the Raoult's law. And if this solution is also following Raoult's law, this PA has to be proportional to XA, or this PA has to be equal to P naught A XA products. This is what we know from the Raoult's law. So what we find is, therefore, the vapor pressure of the solution will be, that will be only A, P naught A XA. This is what is the formula we have for the solutions which are having solid solutes. That the vapor pressure is actually proportional to the mole fraction of the solvent in the solution, and proportionality is opened by the vapor pressure of the solvent in the pure state. We can show that this formula is valid by drawing a graph. If the solution which is having a solid solute, which is actually going to follow the Raoult's law, the graph between the mole fraction and the vapor pressure when plotted, like we are taking only the solvent from 0 to 1, it should go like this and it should reach P naught A. So one must understand that the vapor pressure of the solution, because it's, if its mole fraction is 0, vapor pressure is 0. As it is increased to 1, if you are taking it to a pure solvent, it can reach to the maximum value of P naught A. This is what is the vapor pressure, how it should vary. As stated previously, as per the Raoult's law, it should vary linearly with the mole fraction as indicated, and this is what is being proved by this formula.